The points A, B, C, D are graphed as shown. The line L has the equation x equals 3, and the point Q is a reflection of C and L. Point P is a reflection of D and L, R is the reflection of B and L, and S is the reflection of A and L. State the coordinates of P, R, and S. Where is P, R, and S? Okay, so we got to reflect D and L. So here's L right here, up top. That's L, and then there's D. So I guess 1, 2, 3, 4. So 1, 2, 3, 4. So that point right here, I guess would be 3, 4, 5, 6, 7. So 7, and then 1, 2, 3, 4. So 7, 4 would be the coordinates of P. So very similarly, you're going to do the same thing for B and L. So where's B? B's up here. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 the other way. 1, 2, 3, 4, 5, 6, 7, 8. And that's going to make it 11, right? Yeah, 11. And then 1, 2, 3, 4, 5, 6, 7 is the y coordinate. So that's going to be R. So that's R. And this guy was P. And then finally, the S is the reflection of A in L. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And that is going to be obviously 11, 0. And that's S. Calculate the perimeter of ABCD PQRS. So let's connect the dots and let's see what kind of shape we get. So we have A to B, A, B, C, down to D, then P, Q, R, and then S. S is all the way at the bottom, right? Okay, so that's the shape of so the perimeter shouldn't be that difficult. That's 7, that's 4, that's 3, that's 8, 3, 4, 7, and 16. So when you add it all up, you will get 52. And part C, we have figure ABCDPQRS is rotated around the line L to create a three-dimensional solid as shown. This solid is a larger cylinder with small cylinder removed. Determine the volume and the surface area of the solid. Okay, so let's do the volume first because I think that might be slightly easier. So the volume of this shape is basically the volume of the big guy minus the volume of the small one. So the volume of the big one, we'll just put pi big R squared big H, and then pi small r squared small h. So let's substitute all these in. The big radius is 8, the big height is 7, and the small radius is 4, and the small height is 3. So this basically, you can do this math fairly simply, and that's going to be 400 pi. So that takes care of the volume. Now surface area is a little bit more complicated. Okay, so let's break this down by steps. So first, I'll just write it. The bottom circle, that guy. So that's this one right here. And then the next one will be I guess the entire, all the sides. So the entire side. I just want to write it out so you know what I'm doing. And then the next one after that would be the top. But the top is basically big circle. So circle big minus circle small. Right? Because you got to subtract the small circle because that's been cut out. And then after that, you're going to add actually that one because that's part of it. Plus circle small. And then I think the last one is the inner side. Yeah. So the inner side. Okay, so let's do it. Bottom circle would be just pi r squared, so that's going to be pi 8 squared. The entire side, that's going to be 7 times the diameter. Oh, sorry, not the diameter, the circumference of that circle, which is pi d, and d is 16. So pi times 16. Now these two interestingly cancel out, so that way you don't have to do them. You just have to calculate circle B, the big circle. That's going to be pi r squared, which again is 8. Yeah. And then the inner side, let's see, that's going to be 3 times the circumference, which is going to be pi times 8. And there you go. And when you do all this math, it becomes 264 pi. That's the total surface area. In each part of this problem, cups are arranged in a circle and numbered 1, 2, 3, and so on. A ball is placed in cup 1, then moving clockwise around the circle, a ball is placed in every 9th cup. The process ends when cup 1 contains 2 balls. For example, starting with 12 cups and placing a ball in every 3rd cup, balls are placed in order in cups 1, 4, 7, 10, 1. There are 12 cups in the circle, and a ball is placed in every 5th cup, beginning and ending with cup 1. List in order the cups in which the balls are placed. So every 5th cup, right? Okay. So the first one, then the 6th one, then add 5, 11th one, and so on. And then if you add 5, it'll be 1, 2, 3, 4, 5. So then the 4th one, and so on, right? So it'll be 1, 6, 11, 4, and then you just keep adding 5, 9. And then 9, if you were here, then you're adding 5, you'd go 1, 2, 3, 4, 5, you end up at 2. Then add 5, 7, add 5, 12. If you're at 12, you go 1, 2, 3, 4, 5, end up at 5, and so on, right? You guys get the point. 10, 3, 8, and then eventually you get back to 1, and that's when you stop. So this is a list of all the cups where the ball would be placed. Part B, there are 9 cups in the circle, and a ball is placed in every 6th cup, beginning with and ending with cup 1. List the numbers of the cup. Okay, same kind of story. So let's make 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So every 6th cup. So we are starting with 1, right? Okay, so 1 is the first guy. Then 1, 2, 3, 4, 5, 6. So then 7. Then 1, 2, 3, 4, 5, 6. Then 4. Then 1, 2, 3, 4, 5, 6. And then back to 1. There you go. So that ended pretty quickly. So list the numbers of the cups that do not receive the ball. So 1, 7, and 4 were the only ones that received. So the ones that did not receive, so did not receive, were 2, 3, 5, 6, 8, and 9. Those 6 cups did not receive the ball. Part B, or C actually. There are 120 cups this time in a circle, and a ball is placed in every 3rd cup, beginning and ending with cup 1. How many cups do not contain at least 1 ball when the process is complete? Explain how you got your answer. So I'm not going to draw the diagram with 120 cups, but if it's every 3rd cup when we're starting with 1, then obviously it's going to go 4, 7, 10, and so on, right? All the way eventually to 115, and then 118. And then 121, but there is no 121th cup. It would just go back to 1 again, and then the process would stop. So these are all the cups that the ball goes in. Yeah. So when you count those, it's 40. And there's 120 in total. So 40 received a ball. So the others didn't. So 80 did not receive. And that's pretty much all that is, I think. And finally, part D. There are 1,000 cups in the circle, and a ball is placed in every 7th cup, beginning and ending with cup 1. Determine the number of the cup in which the 330th ball is placed. Okay, so let's make a list here. We have the ball number, and then we have the cup number. So, for example, the first ball is placed in cup number 1. The second ball is placed in cup number 8, right? Because it's every 7th cup. And the third ball would be cup 15, and so on. So, boy, oh boy, oh boy. So 1,000 cups. And what do they want? The 338th ball. Okay, so this is what we're considering. That's going to be the 338. And we got to figure out the matching cup number. Okay. But there's only 1,000 cups. So this thing kind of, several ways of doing this. I'm just trying to think what is the easiest way. Let's see here. I think just a basic extrapolation is sufficient. I don't think there's anything really fancy. So let's just do that. So dot, dot, dot. Eventually, if you keep adding sevens, you will eventually end up at 995. And you can do this with your calculator fairly simply. And that's the 143rd number. Now, the only problem is that we don't keep going beyond 1,000 cups. It goes back. So the next one, if you add 7, it would be 1,002, right? But there is no 1,002nd cup. It would be the second cup because you just go back to 1 and 2. You see what I'm saying? Because after 1,000 cups, you just repeat it because it's a circle. So this would be the 144th ball. And then add 7 again, that's 9. So it would be the 145th ball. And then you just kind of keep going like that, adding 7s. And eventually you get to 996, I believe, and that is the 286th ball. And then similarly, if you add 7 again, you get to 1003, but there is no the 1003rd cup. There would be the third cup, and that is the 287th. And then the 288th would be 10 because you're adding 7. And then you just keep adding 7s, and then eventually you would get to the 360th, which would correspond with the 338th ball. And this is the number that they're looking for. So I think that's it. Just a basic extrapolation by adding 7s along here. And this just keeps going up by 1 each time because you're just adding the number 1 because of the ball number just increasing. And I think that's it. The positive difference list, PDL, of a set of integers is a list written in increasing order of the positive differences between all positive pairs of integers in the set. For example, the set 2, 5, 12 produces a PDL consisting of 3 integers 3, 7, 10, which are distinct, while the set 3, 4, 6, 9 produces a PDL consisting of 6 integers 1, 2, 3, 3, 5, 6, which are not distinct. What is the PDL of the set of integers 3, 6, 13, 21, and 32? We'll do this on the side here. So 6 minus 3, 13 minus 6, 13 minus 3, 21 minus 13, 21 minus 6, 21 minus 3, 32 minus 21, 32 minus 13, 32 minus 6, and 32 minus 3. So these are all the positive differences. And well, these are going to be 3, 7, 10, 8, 15, 18, 11, 19, 26, and 29. And therefore, this is the PDL. And you can write it in increasing order in this nice little bracket format if you want. B, suppose that x is greater than 16 and the sum of the integers in the PDL set of 1, 4, 9, 16, x is 112. Determine the value of x. Okay, so pretty much we're doing the same kind of story. 4 minus 1, 9 minus 4, 9 minus 1, 16 minus 9, 16 minus 4, 16 minus 1, x minus 16, x minus 9, x minus 4, and x minus 1. So this is going to give you 3, 5, 8, 7, 12, 15, and so on, right? So these guys are your PDL, members of the PDL. And I guess that they're saying that the sum is 112. So add up all of them. So it would be 3 plus 5 plus 8 plus 7 plus 12 plus 15. And then all of those would be 4x. Let's see here. 1625 is 25 and 30. So it would be minus 30, I believe. And that whole thing adds up to 112. So this becomes 4x plus 50 minus 30 is 112. And you guys can do this. 4x is 92, and then x is therefore 23. State of set of integers of the form 3, QRS 14 with 3 less than Q less than R less than S less than 14, for which PDL contains no repeated integers. No repeated integers. So very similar to before, we'll first create that list. So it'd be Q minus 3, R minus Q, R minus 3, S minus R, S minus Q, S minus 3, 14 minus S, 14 minus R, 14 minus Q, and finally 14 minus 3. Okay, great. So how does this help us? Boy. Well, let me just look at the basic ones. What I mean by basic is sort of the Q minus 3, and then the R minus Q, and then the S minus R, and then the 14 minus S. I'm going to look at just those ones. Those are sort of the differences if you're kind of going from one number to another like that. And they all have to be different, right? Because you can't have repeated integers. Yeah, all of these numbers have to be different. So, okay. Well, first let me just add them. Q minus 3 plus R minus Q plus S minus R plus 14 minus S. If you add all of these, some of these cancel. Actually, they all cancel, and the only thing we're left with is 14 minus 3? Yeah, which is 11. Huh, interesting. Okay, so that means that if you add up these four numbers, you get 11. Now, since they're all extinct, not extinct, distinct, different, that means that we can easily kind of come up with a finite list of what the possibilities are. Like, for example, four numbers that add up to 11. Let's see, 1, 2, 3, 4. That would add up to 10, right? So how about 1, 2, 3, and 5? So these guys, so 1, 2, 3, and 5. So for example, if this was 1, 2, 3, and 5, that would add up to 11. Yeah. That would work. Okay, let's see. Let's see if that specific arrangement gives us what we need. If Q minus 3 is equal to 1, that means Q is equal to 4. If R minus Q is equal to 2, that means R would be equal to 6. If S minus R is equal to 3, that means S would be 9. And if 14 minus S is 5, that means S is 9. Oh, or actually, wait. Yeah. Is that good? Is that acceptable? Well, I guess the only way I can figure that out is I have to figure out all these other ones. So R minus 3 would be, well, actually I have to figure out what these values are. So R minus 3 would be 3. Oh, there you go. Immediately we got a repeat. We have to have no repeated integers. Okay. Okay, I got it. So I'm going to stick to the 1, 2, 3, 5, but I have to come up with a different order. So what I mean by that is, you see how I chose 1, 2, 3, and 5. I've got to come up with a different order. Okay, so let's see. Let's stick with 1 here. Let's put a 2 down here. Let's put the 3 here and put the 5 there. And then let's see what happens. So that makes Q equal, well, Q is going to be 4 again. R would then be, R minus Q is 3, so R would be 7. S minus R is 5, so that means S is 12. And then, yeah, so this works, so S is 12. Okay, so let's figure out all of these other guys. R minus 3 would be 4. S minus Q. S minus Q is 8. S minus 3 is 9. 14 minus R would be 7. 14 minus Q is 10. And 14 minus 3 is 11. Is this all distinct here? Let's see here. 1, 2, 3, 4, 5, 6. There's no 6. There's a 7, 8, 9, 10. Yeah, it's all distinct. Okay. So this set of 3, 4, 7, 12, and 14, that one gives a PDL that has no repeated integers. All right. And there's others. You know how here in this one I noticed that I did what? 1, 3, 5, and 2, right? You can get others with the following combinations. 3, 1, 5, 2. So 3, 1, 5, 2. And then you guys can figure that out. I think they only wanted us to come up with a set, but you can come up with others. Another combination that would produce it would be 2, 5, 3, 1. And then finally, 2, 5, 1, 4. 2, 5, 1, 3, I believe, is the other one. Okay, so that takes care of part C. Prove that the PDL of every set of integers of the form 3QRST with 3 less than Q less than R less than S less than T with T less than 14 contains repeated integers. So the same kind of story, I'm going to use the 4 basic differences, the Q minus 3, the R minus Q, the S minus R, and the T minus S. And let's add them up. So we got Q minus 3 plus R minus Q plus S minus R plus T minus S. And when you add these up, a lot of this stuff disappears, and the only thing you get left with T minus 3. Now, they have told me that T is less than 14. So that means if T is less than 14, that means T minus 3 must be less than 11. Yeah. And then if it's less than 11, well, the minimum it could be is 10, because these are all different, right? If you look at this inequality, they're all different. So the differences have to be unique. These 4 have to be unique. Later, you could probably get some doubles with some of the other members of the PDL. But these ones have to be unique. And even if they were unique, the smallest you could get was 10. Like if it was 1, 2, 3, 4. 1, 2, 3, 4. The smallest sum would be 10. So T minus 3 has to be less than or has to be greater than or equal to 10. So that basically means that T minus 3 is equal to 10. That's the only possibility. So therefore T is 13. Only possible value for T. Okay. All right. So if that's the case, I think we can figure out everything else. If T is 13, then T minus S is 4, so that means S would be 9. And then S minus R is 3, so that means R is 6. And then R minus Q is 2, so Q would be 4. So my list is 3, 4, 6, 9, and 13. That's my list of numbers. And what did they ask? Show that it can pay. Okay, so the entire PDL has to contain repeated numbers. Okay. Well, I guess I have to show the entire list. Well, the entire list, let's see here. We had Q minus 3, R minus Q, R minus 3, and so on. So Q minus 3 is 1, R minus Q is 2, R minus 3 is 3, And then let's see here. S minus R is 3. Well, there you go. We just showed 2 are repeating, so that proves it. Now you might think, well, are there other scenarios? And the answer is yes. This is not the only scenario. For example, here I just gave it 1, 2, 3, 4 like that order. But there are other scenarios, and I'll list them here. Other, I guess, options or categories or whatever. The other way is if you put a 1 adjacent to a 2 or a 3. So you could have like a 1 and then a 3 and a 2 like that. Or the 1 is not adjacent to the 2 or a 3. So the 1 is just adjacent to 4. And then you'd have a like that. 1, 4, 3, 2. Yeah. So for each of these, you can calculate the PDL and then show that it also contains repeated integers.